Okay, I guess we should probably start, yeah?
Okay.
So welcome back, everyone. Thanks for coming back, and thanks to the new round of speakers for accepting the invitation and speaking from different time zones at this workshop. First speaker is going to be Josh Falk from UBC, and the work is their recent work on twisted double bilayer graphene. If you have questions during the talk, please raise your hand or speak up, and I will alert Josh that question is coming. Please, Josh.
Perfect. Thank you very much. Thanks to all the organizers from UBC and Rice. It's great to have this opportunity to talk about this material that's been our sort of favorite little playmate since for the last 2 or 3 years. Twisted double bilayer graphene. I'll start with the acknowledgements. So this was really a material that was let's say pioneered or in the group, at least cheerleaded in the group by Manab, who was our QMI postdoc and really sort of convinced us to get going. And then he's been gone for almost half a year now, but the measurements he started were carried on by Chris Coleman and another postdoc and Jin Chang, a new PhD student. And then most recently, the data that I'll show you at the end is from a fantastic undergrad, Ray, who really motivated himself, the sort of experimental trick that made the final results possible. So anyway, this is really, I feel like, in general, as a group leader, I play somewhat of a sort of supervisory and also directing role in the group, but this is really a project that's been, I've tried to be, supervisorial and wise when I can, but it's really been led by the students. So I'm really grateful for that. And then there's the theory has been critical for this. I mean, as always, but especially in this case, I'm really new to the field of 2D materials in general and twisted graphene specifically. So we've really counted on our theory collaborators, both at the University of Texas, Alan and his postdoc and student, and then Andrew Potter at UBC has been also helpful, and Marcel. And then Ziliang has been great at really helping us with the most critical tricks of making these twisted samples, and Dong Yang, and Ziliang's other students as well. And then, of course, we count on great HBN from our Japanese collaborators. Okay, so just a quick outline of the talk. I will give a brief introduction to twisted double bilayer graphene, but by now probably this audience has all heard many talks about twisted graphene systems, so I'll try to just alert you to sort of what's different in twisted double bilayer. And then sort of the one sort of ubiquitous characteristic of twisted double bilayer is broken symmetry states. So I'll describe a little bit what that means, how it's special in twisted double bilayer to some extent. And then our standard probe is magnetoresistance. So just standard conductance measurement in a whole bar geometry, and then just looking at what that can tell us, especially as a function of magnetic field. So first I'll show you some anomalous Hall data that I think we understand well, and then some more magnetoresistance that is a complete mystery to me. And then at the end, I'll show our most recent result, which is that this material, which many people thought would superconduct from the very beginning because it's so similar to twisted bilayer graphene, but then turned out not to superconduct. Now it turns out to superconduct if you do the right things to it. And so I'll show you that data. Okay, so first of all, twisted graphene. Again, this doesn't need much of an introduction for this audience, but the basic idea is you start with graphene, which itself has very interesting band structure, these Dirac cones that have built-in topology. And then you put 2 of these sheets right next to each other and you twist them. And so you end up with 2, well, in the case of monolayer graphene, 2 Dirac points that are right next to each other in a momentum space. And then these hybridize, and you end up with very flat bands right at the point where these 2 Dirac cones hybridize. And so in twisted bilayer graphene, so that's a monolayer and a monolayer with a twist, then you end up with the whole family of exotic states that you all have, I'm sure, heard about and read about: correlated insulators, superconductivity, whether it's conventional or unconventional, the jury's still out, ferromagnetism, quantum anomalous Hall effect, fractional turn insulators. The story goes on. So you might ask, what are the critical ingredients that make this very exotic, but at the same time fairly single particle like material act in all these exotic ways? So you might say, well, it's just the flat bands, just a monstrous density of states. That might be right. There's also topology built in. There's maybe other things we don't know about. So now let me switch a little bit to the system I'm going to be talking about, which maybe can help us answer some of these questions. So that's twisted double bilayer graphene. So instead of starting with two monolayers, those give you these nice Dirac cones, this is two bilayers. So a bilayer and then another bilayer, and you twist them. So that's twisted double bilayer. And so instead of Dirac cones to start with, you have Dirac paraboloids or something like that to start with, but otherwise fairly similar band structure. But the special feature of twisted double bilayer is that because you don't have simply a single set of AB sites, you now have two offset. Then by tuning the vertical electric field, so the electric field across the across the bilayer of graphene, you can change the original band structure from being two hyperboloids that touch to flattening out the place they touch and creating a gap, and you get this Mexican hat geometry eventually. So the point is, building on twisted bilayer graphene, you now have the added tunability of that starting band structure. You can now tune it with an electric field, and then you add the twist, and so then you have two of these right next to each other in momentum space, and they hybridize, and so then you can play your games. So one big advantage of twisted double bilayer, in addition to just this general tunability, is that there is no single magic angle, unlike twisted bilayer graphene. So there's a whole range of angles over which you can get flat bands. And whether they're exactly as flat as in monolayer, I think probably not. So people say that the bandwidth in monolayer is something like 5 millieV. In double bilayer, it's maybe, well, according to this graph, 7. It's somewhat worse, but not categorically worse. And you have this added tunability. So that was one thing that got us very excited about it in the beginning. Okay, so let me show you this a little bit graphically. Again, from the starting point of bilayer graphene, you apply a displacement field out of the plane. You have these two hyperbolas that touch, and then when you apply the vertical field, you get a gap between them, and they each are flat in and of themselves. So in the last year or two, there's been very exciting work starting out of Santa Barbara, where they discovered that just this flat bottom of the hyperbola that you can get in bilayer graphene can give you all kinds of correlated effects as well. But we're not looking at just bilayer. Now we're going to sort of marry the flat bands that you get in bilayer with the ability to also add extra flatness from the twist. So then you start with these two hyperboloids here, and then they hybridize. So you get bands that are, well, let's say at least a little bit flatter and isolated, but not that flat yet. And then you apply an electric field and you can flatten them further. So this is still waving hands. But the point is you've taken a system which is now more tunable than twisted bilayer graphene, in which you can still probe all of this same correlated physics that comes from having a narrow bandwidth compared to the interactions. So this work on twisted double bilayer graphene has been going on really since 2019. And very quickly, it was discovered that just like this, or very similar to this correlated insulator state you get in twisted bilayer graphene, you can get something at half filling of the band in twisted double bilayer. So I'll show you pictures like this in the next few slides. You'll get to know them a little bit better. But basically, this axis here, if you see my laser pointer, is the electric field across the graphene. And this axis here is the filling. So this is zero density, essentially. This is between the conduction and valence band. this is a fully filled first conduction band. And so these states here are the correlated insulators in twisted double bilayer graphene. So these are what people noticed at the very beginning, and were the beginning of this here, the top later states, and also this state and of this.
Okay, sorry, we seem to have lost Josh. Let's see if he manages to come back.
I'll send him an email link so he can get back in easier.
It's too bad that you're not here, so otherwise you can take a break and get some cookies from Alana. So we lost you as you were describing the first plot on that slide.
Okay.
Still a little bit sketchy, the connection. Yeah. Yeah, maybe we should cut your video.
The audio is sketchy.
Yeah, I was suggesting to maybe try without video and just share the slides and see.
Yeah, let's try this. Well, this is. Let's see if this works any better. Well, this is probably a.
Interesting. He was doing okay for.
Yeah. Well, I wonder if he's in some guest house or so. Or there is any other connection you can use, but.
Well, Okay, I don't know how this will work, but let's try one more time. Now I'm broadcasting from my phone, so.
Okay.
Let's see. All right. All right. So let's see. I guess the point from, I'm not sure how far we got here, but the point is twisted bilayer has been measured by, yes?
Yeah, you were discussing the first plot, the bottom left. And,
right. Okay.
So
this halfway between this line, which is zero filling, and this line, which is full filling, we'll get to in a moment. But this states here are the correlated insulator states that really confirmed that twisted double bilayer is indeed showing you these strong interaction effects. Okay, so right now I want to help you sort of navigate these 2D plots. I started by arguing that this material is much more tunable because you have gates on the top and bottom, which allow you to tune the out of plane electric field. That's this axis. So of twisted double bilayer as a function of filling and out of plane electric field. So to start with, we have right now, well, so first of all, at the same time as I show you this resistivity plot, I'm showing you the band structure that's calculated by Jihang.
Josh, I think we're losing you again a bit. So, you know, your voice comes and goes.
And down here, that's the first valence band, and this is the first conduction band. Okay, and so as we increase the filling now, we're moving across from the fully filled valence band to the fully filled conduction band. And so you see these bright red lines when the first conduction band is fully filled. That's because you're in a band gap. And then we started with the first valence band fully filled. So that was down here, that was another band gap. And so as we move across here, we're moving the Fermi energy up across these two. Okay, and then we can instead do the same with a perpendicular electric field applied along the sample. And so again, we're going to increase the Fermi energy from below the first valence band to above the first conduction band. But now you see these bands look a little bit different because now we have this out of plane displacement field. And so in particular, you can see that this first conduction band is quite a bit flatter. Okay, and so now if we start with that yellow dot down here, then we can start adding some electrons. We're filling the valence band. Then we get to the band gap in the middle, and we start filling the first conduction band, half filled, and then fully filled. And so you can see this state right here when the first conduction band was half filled. That's a correlated insulator state. It's the same place that you would expect a Mott insulator, but the origin of this resistive state seems to be broken symmetries, not a Mott insulator. So we'll talk about what that means in a few slides. Okay, and so here, again, that's that half-filled state when the Fermi energy is right in the middle of this flat band. Okay, so we're going to focus on this region here. That's where the correlated insulator, or the correlated behaviors are most prominent. Why in this particular region? Well, if you're at a lower electric field than this one here, you notice that this resistive state here at zero filling is not resistive anymore. We've lost the band gap between conduction and valence band. So the first conduction band is not separated from the first valence band. Above this electric field here, even though you don't see it in the resistivity plot. The first conduction band overlaps with the second, and so again, it's not isolated. So only within this region here, you have a fully isolated conduction band, and then you can slowly fill it right there. Okay, so you have this insulating state at half filling. You can see a tiny little insulating state here at 3/4 filling. And then if, so this looks fairly similar to what's seen in twisted bilayer graphene, but unlike twisted bilayer, where the stories at the beginning were about correlated insulators, in this case, it was pretty clear from the, sorry, were about mod insulators. In this case, it was pretty clear from the beginning that, that this was something more like quantum Hall ferromagnetism that was creating an exchange splitting between bands. And so if you look at the origin of these insulating states, it really seems to be that fourfold degenerate band that you started with, that spin and valley degeneracy, splits into either 2 or 4 bands with a band gap in between each of them. So that seems to be the origin of these insulating states. However, if you start with these 4 bands and then they're split, you can ask how they split, right? You have 4 degrees of freedom, you have 2 of spin and 2 of valley, but they can, of course, combine into whatever spinners you want. And so then, you know, how exactly do these states combine? And that's been one of the big questions in the field is what is the nature of these broken symmetry states? So that was where our experiment started. I'm pretty late already. But Manab made these 2 twisted samples, twisted double bilayer samples, standard Hall bar geometry, top and back gates. We use a graphite back gate for higher mobility. And then when you measure, you see again these regions here of which have previously been associated with these correlated metals and correlated insulators. And that's really where the story starts, really trying to map out what is the nature of the broken degeneracies in these regions here. And so we can divide these really into 3 different behaviors in 3 different regions. First of all is outside of these correlated areas. So that's like where this circle is. You see magnetoresistance that looks basically just a parabolic magnetoresistance like a metal. Nothing very interesting there. The Hall resistance is just flat. Within this correlated region here, but where it's still metallic, then you see this very sharp dip in the magnetoresistance. That might remind you of anti-localization, but it's almost certainly not. We're not sure what the origin of it is. There seems to be weak localization right at the center, but I'm not going to dwell on that here. The point is they're characteristically different behavior than what you get outside. But I don't have yet a clear answer to what's going on there. Then in this 3rd region, right up here, there's still a different categorically different type of magnetoresistance. And there you get these very sharp hysteresis curves. So the white and yellow traces refer to sweeping up and back in magnetic field. And so you have these sharp jumps. And the Hall resistance shows you these nice open hysteresis loops. So this was clear signature of anomalous Hall effect. For those of you who've seen this in other systems, basically the characteristic signature of anomalous Hall effect is if you tune to 0 magnetic field, you can get a finite transverse resistance, which flips sign depending on the magnetization in your sample. And so apparently by coming from one or the other magnetic field, you can have a built-in magnetization. Okay, so in order to get this anomalous Hall effect, you need first of all broken time reversal symmetry, and second of all, finite Berry curvature. So finite Berry curvature has been predicted theoretically, although it was not confirmed until this. And then broken time reversal symmetry, this then helps you understand which broken symmetry states are possible in this green region here. Here, where you have this weak localization characteristic, time reversal seems to be intact, although as I say, there's more mysteries in terms of what's happening here. And out here, things seems to be more or less non-interacting. Okay, so I'm gonna go through the rest of this very quickly since I lost a lot of time with my IT. If you compare the in-plane and out-of-plane field dependence of these hysteresis loops. There's an enormous anisotropy. So basically, in-plane field does almost nothing. The hysteresis is entirely generated by out-of-plane field. So that's telling you that this must not be spin magnetization, which would be more or less isotropic. It must be orbital. And so that tells you that it's valley polarization within this last corner here. There is, at the same time, even though I said the in-plane field does almost nothing to this hysteresis, it has an enormous effect on the resistivity. And I'm just going to flash through this part because we really don't understand it, but I would love if some of you have some ideas about what kind of effects might generate this. I'd be very interested to hear. So if you're looking in this region of gate space where you have broken time reversal symmetry and you sweep the in-plane magnetic field, there's not really hysteresis of the same form, but you see an extremely sharp dependence, just a few millitesla of in-plane magnetic field. So this corresponds, normally we think of in-plane magnetic field as primarily affecting the spin. This corresponds to a few nano EV of Zeeman splitting. So it's way too small to be any kind of single particle spin effect. And you really have no idea what is the origin of this effect. It seems it must be some very strong spin valley coupling, but spin valley coupling in a way that creates, well, I don't really want to speculate more because at this point it's still a mystery to us. Okay, so this is more of this sort of mysterious in-plane field dependence. It's extremely sharp. There's jumps. They seem to be very dependent on where you are in the sample. So if we look at different contact pairs, you get different jumps. So it really seems to be something about domains that are created in the sample and jumps between domains that are affected, that are driven by in-plane field. This is one of the big mysteries we're trying to solve now. Okay, but in the last few minutes, I want to just very quickly show you the most recent sort of amazing thing that's appeared to us in this material. So I showed you a picture that looked like this of the resistivity as a function of basically top and back gig, but I rotated my axes, so that's electric field and filling. And if you look, this is where we first noticed it. If you look here in the valence band, you see really nothing, which is what was expected in the valence band because it's not very flat. You can see here it's pretty wiggly. And so you don't expect much correlation effects. No one else saw any correlation effects. And then Ray was very excited about trying to put WSE2, tungsten diselenide, right next to twisted double bilayer graphene in order to induce a spin orbit interaction. And so we did that.
Josh, still there? We lost you.
You end up with this dark blue little pockets. We've now done this in, well, okay. So first, if you look more carefully at that dark blue pocket, dark blue corresponds to very low resistance. And if you zoom in here, you can see that really it's very, very low resistance. It ends up being superconductivity, but it's so first of all, this angle again with WSE2, and again, so this is 2 out of 2 samples we've made with WSE2. We never saw this without WSE2. You get dark blue pockets. This one's in the valence band. This one's in the conduction band. This one, the resistance went to about an experimental noise of 0. And so apparently we found these little pockets of superconductivity in twisted double bilayer graphene. You may ask why in these particular regions, and I think that's a crucial question. All I can do is give you maybe a little hint of let's say, a correlation at least. So if you look at this 2D space and you look at this interesting difference, which is the Hall filling versus the total filling. So this tells you basically how many active carriers there are versus how many, versus how many total carriers there are. So if you look in regions right near where this superconductivity is located, so the superconductivity is right here and right here, you see these regions that are appearing white here, where there is apparently some spin and or valley polarization that's appearing exactly at those locations. Well, no, I shouldn't say exactly at those locations, right next to those locations. And so here we have this region, the valence band, and if you increase the in-plane field, you get spin polarization. Here in the conduction band, if you move the gate voltage just a little bit, you get valley polarization. So I'm not sure the causation, but at least there is a correlation between these superconductivity regions and regions of isospin polarization. Isospin just means sort of a generalized spin, maybe spin or valley. Okay, so I'll stop. I'm sorry, I've gone way over. I guess the take homes are, first of all, twisted double bilayer graphene. You have this enormous gate tunability and flat bands, which allows you to really tune between different broken symmetry states. Some of them we understand, a lot of them we don't, and are really, I think we're very completely stumped about what might be giving these signatures we're seeing. And then the third one is that included in these somewhat mysterious effects, immediately next to these regions of spin or valley polarization, you can find superconductivity. With that, I will leave you. And again, apologize for going over.
Thank you, Josh. Thanks so much. Yes, very interesting, despite the challenges. Questions, if we can take a couple of minutes. Anyone? I have one, but I wanted to give priority to other people because I can ask you anytime. I don't see any questions. I'll ask you one quickly, Josh. I was wondering, when you in this field, when you talk about correlated insulators, is perhaps the only situation where you could change, with your bias, tuning the doping basically across these bands. And when in other systems like cuprates, when you tune the doping, you see this transfer of spectral wave. So if you dope, upper and lower upper bands, you can see a transfer of spectral wave that goes with twice the number of carriers you induce. And this is directly a sign of really the correlated nature, the relation between the high energy and the low energy physics. Is this something that one can look at here as you change your bias? Can you see effectively a transfer of spectral wave, a transfer of states at a rate which is higher than the number of carriers you introduce?
Well, so first of all, let me just say that in twisted double bilayer, you can tune not only the filling, but you can also tune the flatness of the band. Mm-hmm. So you can in a way tune the strength of the interactions in that way. So that's one of the things I like about twisted double bilayer as opposed to twisted bilayer. However, if you ask about this transfer of spectral weight, so we haven't seen a situation in which you're actually inducing more carriers than you would induce, let's say, by the doping. But what we've seen is that you can change, this was related to this last slide I was showing about this, these polarized regions versus unpolarized. When you're filling 4 bands together, then you end up, let's say, maybe with 4 half-filled bands. And then you may find that you go through a transition, and then that turns into 2 fully filled bands and 2 unfilled bands. And so in that sense, I'm not sure if that's the same language of transfer of spectral weight, but you can find that the amount of band filling does not increase sort of uniformly with gate voltage. Some bands move up and some bands move down.
Okay.
In their
Thanks.
filling.
Thanks, Josh. I see, Shimiao, you have a question?
Yeah, so just a sort of general characterization type of question. So I think in twisted bilayer graphene, spectroscopically, it's being estimated that the strength of interaction roughly is on the order of the bandwidth for the Maury bands. And I wonder whether in this twisted double bilayer graphene case, whether the relative strength of interaction is stronger or weaker.
I think it's, I mean, within factors of 2, it's the same.
Okay.
I mean, the spacing between carriers and distance to screening gates and things like that. The electrostatic environment is very similar, so I guess the interaction strength will be roughly the same. Mm-hmm. The wave functions are slightly different, but the Coulomb interactions, I guess, will be similar, and the bandwidth is similar.
And if you estimate the gap on the insulating side, is that roughly also the same as twisted bilayer graphene case, or is it somewhat different?
I think in general, the gaps on the let's say the separation between the first conduction band and higher bands is, if anything, stronger in twisted double bilayer. But again, it's very tunable by gate voltage. Mm-hmm. So you could get situations where there's mixing with higher bands, or
I meant like something like the partially filled commensurate filling case, the correlation driven gap.
Oh, I see, the correlation driven gap. Well, I don't actually know. Mm-hmm. The gap in twisted bilayer graphene. In twisted double bilayer, it's scales of a few tens of Kelvin.
Okay.
We have to move on. There is one question in the chat from Chris Holmes, and maybe I can read it to you, Josh, and you can answer very quickly. Say, what is the nature of superconductivity? Is this a 2D system or quasi 3D? So costally tailless or versus BCS-like?
It's definitely 2D, and therefore costless tailless. However, I guess when people in the twisted double bilayer or twisted bilayer camp talk about BCS, it's often more in the context of phonon driven and or conventional versus unconventional, and there I think the jury is really still out.
Okay, thank you so much, Josh. And
thank you. I'm sorry about the IT problems.
Yes, no worries. Yeah, that's what you get with Zoom.